All right. So you have seen the cells that I've drawn, which are right there, but it's kind of unfair to think of cells on that scale. I mean, obviously, we don't have any cells that are as big as an ironing board or a bookshelf. See, I got another whiteboard there. Stack of whiteboards there where the weights are. Some more whiteboards down there. I got quite a few. Anyways, when we're thinking about cells, we don't want to think of them on that size. We're going to look at them on a little bit of a smaller scale. Okay, so it doesn't make sense to look at a cell the size of an ironing board or whatever else you want to compare it to, because cells are tiny. They're very tiny, as a matter of fact. Now, this is one of my drawings because you know I like the art and you know I like the science. So we got a little bit of a combination here. And right here, I've got a bacterial cell. And that bacterial cell is a whopping 5 micrometers. So we have 5, and this is what micrometers looks like. It's the funny little U, and 5 micrometers. That's a bacterial cell. If we want to think about that in perspective, right over here, we have an egg cell, and we have a sperm cell. Now the sperm cell is, from head to tail, actually flagella, the sperm cell is 30 micrometers. When you want to think of the biggest a cell truly wants to be to function somewhat efficiently, we can think of an egg cell. Because an egg cell is going to be more like 100 micrometers. Now, to put that into perspective for you, 100 micrometers is about the width of a human hair. At that size, we could see an egg cell, but it would be very difficult to spot, and we would really have to be looking. Now, surface area to volume is a very important concept. And as you can see to me, so is Dr. Pepper. Both are equally vital. We have some things here when it comes to surface area to volume that are important to consider. That the surface area of a cube is length times width times the number of sides. The volume of a cube is length times width times height. So in order to actually calculate surface area to volume, that's how you do it. And then you take the number you get for surface area and you put it as a ratio to volume. There is a very excellent example in your book of surface area to volume, so I am not going to go over the math. I am going to put the book in front of you. As you can see, little cube, middle-sized cube, big cube. As we will discuss further, there are distinct disadvantages to being this big cube right here. When you think about surface area to volume on the cellular level, it is appropriate to think of the size of people. One might make an assumption that the bigger the person, the bigger the cell. However, this does not hold true. Our bodies have trillions of cells. However, if we have this guy right here, little skinny guy, actually looks like a stick figure, but he's happy, so that's good. And then we have this guy. He's not a stick figure. He's not exactly an overly large guy, but he's much bigger than this gentleman right here. And then we have this guy. This is my Uncle Chuck. My Uncle Chuck had a really large belly. Now the difference between this, and this is fairly simple. When you do something that is physically straining, you're generally going to sweat. But have you ever noticed that the bigger a person is, the more that they sweat? So we run a mile. Sticky here, barely breaking a sweat. Couple beads of sweat down his face, maybe little drips here. He's doing all right. Normie, well, he's sweating a little bit more. As you can see, his t-shirt's a little soaked. He's definitely sweating here. He's got sweat coming off everywhere. Uncle Chuck is a sweaty mess. Looks like he's crying, but really, he's sweating a ton. Because he has more cells, which means more work. As a cell gets bigger, both the surface area and the volume will generally go up. However, the best thing for a cell is to have a higher surface area to volume ratio. The more surface area and the more volume you have, the easier it is to get things done. Let's just say this has a surface area to volume of 6:1, just like your book illustrates. And let's just say this is the bigger version of it, and this has a surface area to volume ratio of 3:2. This poses a large problem when it comes to transport. If something needs to get quickly into this cell, it's got a lot more distance to travel. If a lysosome needs to clean up waste in this cell, it's going to have a lot more work to do than this cell, because this cell has a lot less volume. This cell has a lot more to clean, and because there's so much more in the middle, it's going to take that much more effort. Now, when we think of surface area, let's actually just think that that's you right there. You're in a room, and let's say that I told you that I would give you $1,000 if you could get from that room right there out to the road in less than a minute. Would you take that challenge? However, if you do not make it to the road in less than a minute, you have to give me $100. Seems like a pretty good challenge, doesn't it? So if you took that bet, $1,000 to reach the street in a minute, really there was some trickery involved there. Because I had whiteboards covering up the actual drawing, which isn't a very good one, but this is the Pentagon right here. And to get from this office right here to this street out here is going to take a lot more than a minute. So that would have been a fool's bet. But I set this up to illustrate surface area to volume, which is something we don't talk about that much, but it's going to be very important in any scientific endeavors you have from here on out. In fact, in college, many times, just by answering surface area to volume to a question you don't understand, you might just find you get points. It is that important to just about everything in life. Now, if we're comparing this wonderful drawing of a pentagon here to a cell, well, there's still going to be a need to transport things in and out. And if that needs to happen quickly, it's not going to be very efficient with this cell, which has a ton of surface area, but it also has a ton of volume. Think about it from this little room. If you needed to get an energy drink to the boss at the desk here, and you only had to travel from here to here, that transport's pretty easy. But if you have to get an energy drink to the boss from here to here, your boss is probably going to be sleeping by the time you get there. So, I don't believe we're going to cover the cell cycle too much, but I did want to touch on it just a little bit because there are some important aspects of this that we're going to cover in more depth. And I want to make sure that you at least have a little familiarity with the cell cycle. So I'm going to run through it really quick. You can pause this, you can look at my cool drawings. They're a little busy right now, but I'm going to zoom in on the sections when they matter. So we're going to start with the G1 section, which is the G1 phase. And that is where a cell spends most of its life. That is where a cell creates organelles and proteins. That is where a cell does most of its growth. And that is where a cell carries out most normal functions in the G1 phase. Now from the G1 phase, we go to the S phase. And the S phase is where, well, that's where DNA replication happens. And this is an important part because we're going to be talking a lot about chromosomes. And there is some confusing terminology when it comes to chromosomes. This right here is a chromosome, as we have it. This is a whole chromosome. In the middle, right here, we've got a centromere. That's going to be very important when we get to mitosis and meiosis. Now, I drew this guy blue. There's no reason for it, just because I felt like it. But we've got a little pink one here as well. Because your chromosomes don't just come from your mother or your father, they come from both. Now, something we're going to talk about later as well. However, we're going to be learning words that seem similar. Chromosome, which we're looking at right now. Chromatid and chromatin are yet to come. So in S phase, 23 pairs of chromosomes, they become 46. Now, as you saw, we had a karyotype. A karyotype, which is 23 pairs of chromosomes. It is a little bit weathered because actually I've turned this karyotype board into your submission box for your assignments, which I'm going to post on the wall when I get into class tomorrow. Anyways, 23 pairs become 46. 23 pairs of chromosomes. Once we leave the S phase, we head into the G2 phase. Now, this is where the cell prepares for mitosis. It makes microtubules, or spindle fibers, which are there to split the sister chromatids. So here we go. Now we have another new word, chromatid. We have chromosome, chromatid, and we also have chromatin. A little bit confusing. We're going to talk about them. Don't worry about it. Not yet. Now, part of interphase, and to me, the biggest part of interphase is this little slice of pie right here. And that represents mitosis and cytokinesis. Mitosis is where the nuclear material divides and separates to opposite sides of the cell. Cytokinesis is where the cell actually divides and splits into two cells with identical nuclei. They are called daughter cells, not because they have a mother. They are called sister chromatids. These are scientific terms as well. Okay, so we're going to try to make sense of chromosome, chromatid, chromatin. It is a very confusing thing to think of when they all sound very similar. So we're going to draw a chromosome here. Okay, so as you can see here, drawn a great big structure. And this structure, we're going to go red so that we can show where the chromosome is. Now the chromosome is going to be the whole thing. This is the chromosome. So we're going to write that in red. We're going to say red equals chromosome. So, chromatid with a D, we're going to represent in yellow. Now a chromatid is 1/2 of it. And you'll see when we get into mitosis that this is going to split. However, right now we don't need to worry about that. So as you can see, a chromosome is all of it, a chromatid is half. So we use this to represent chromatid, which is not very legible. So even though that is in yellow, we'll write it in black. Chromatid. Bad choice of colors. Whatever. Anyways, then we have this area down here. That is chromatin. And chromatin is simply unpacked DNA. Chromosome is the whole structure. Chromatid is 1/2. Chromatin is unpacked DNA. Chromosome whole, chromatid half, chromatin unpacked DNA. Get it? Got it? Good. Okay, so that's basically the gist of the lecture for today. Thought I was going to be going into mitosis. I was a little premature, a little early on that. We actually will be covering mitosis over the next couple days, but I had a choice for us to go over cells today or to talk about surface area to volume. And I really wanted to get into surface area to volume because it has a lot to do with cells as well. Now, I'd just like to introduce a concept to you that I kind of want you to keep in mind. And that concept is known as PMAT. Now this phrase, well, not really a phrase, it's an acronym, but it's one that's very important because it's one that's going to come up more than once through mitosis and meiosis. And these are the stages of what we're looking at. So this is prophase. This is metaphase. Next is anaphase. And finally, it's telophase. Personally, and this is just me, I'm a fan, as a student, of making any device that will help you remember something. I don't like memorization, but this is one of the times where memorizations will help you. PMAT is an easy memorization to come across. However, from PMAT, there's an even easier one. Well, not easier, but a little less short. And I like to say ProPhase. met Anna tell. The pro met Anna over the telephone. Pro met Anna over the telephone. PMAT. Any way you need to remember it, do so. However, I'm just trying to help you with a couple ways that may or may not prove beneficial to you. I've had some really wacky memorizing techniques over my time as a student, but I find that the times that I understand it the most is when I actually study it. Thank you.